Okay. Can everyone see my screen?
Yes, yes.
Yes, great. Okay. Right, so today I'm going to talk about an application that I worked on. It's called ToxBlock, and it's basically a simple deep learning application written in Python, which can be used to classify toxic language in text, meaning toxic language like nasty words, insults, something you probably don't want to say to other people if you're nice. So that also means the first thing I'm going to show you is a little disclaimer. So this talk will contain toxic language in English. And if you're sensitive to rude language, then please do not attend this talk and find something else, because it will contain some insults and things like this, but it won't be too bad. I also would like to ask you, if you decide to stay, maybe you could prepare some dirty sentences, some bad language, some nasty insults, because at the end, I want to show you a little demo of this application, and it would be great if we could collect some nasty language which we can then feed into this application. So maybe another question: what is this about? Because classifying toxic language doesn't seem to fit to anything that we do at HDI. And that's true. It has absolutely nothing to do with my work here. I work as a data scientist in the life insurance data science team, but also cooperate with data science teams in Hanover. But usually we don't classify toxic language. We work on things like getting insights about our customers, maybe contract cancellation predictions, recommendation engines, things like this. So this is a purely personal machine learning project of mine, which I did on the one hand to get an introduction to natural language processing, which I hadn't done until then, and I found it quite interesting. So I wanted to do a project to learn a little bit about it. But I also wanted to go through this process of getting a machine learning model from a research stage, where you just explore the data and you start building to the model to the point where you would actually want to deploy it so that other systems can make a use of it. That's something you don't necessarily do when you come from an academic background. So before I started working as a data scientist here, I was working in academic research, and often you just have an analysis which you get out and you publish it in a paper, and you don't have to integrate it in other IT systems. But now working here, that's exactly what I have to do. It has to communicate with a bunch of other systems, and so I use it a little bit as a dry run, because that was something that I was going to do in my actual job here at HDI. But since I already heard in the chat that not everyone is familiar with AI and machine learning things in general, I'm going to show you some fundamentals first. So what is AI and machine learning? Well, AI could be anything. It's not very clearly defined. In our industry, it's often used as a buzzword to sell some product. Everything has to be cool and fancy and has to have some AI solution in it. But what we're, as data scientists working in an insurance company, usually not doing, it's like building apocalyptic Terminator robots or something called artificial general intelligence, where people really try to like build something like a human or even smarter than a human, an intelligence that can comprehend things in general, not specific to one application. So many smart people at universities are working on these things, but that's not usually what we do in our everyday job. Insurance, we would rather use specific statistical algorithms that are specific to a certain application, and we try to do pattern recognition on the data that we have to find insights in the data that you would not see just by looking at it by eye, and then try to predict something that is useful for actual business use cases. And this is what we call machine learning, by the way. It's a little bit more specific than the very broad term AI. And there are many types of machine learning that you could potentially do. I would say there are three main categories. I also found this in a nice blog post. Someone interested to read a bit more about this. Three main categories in which most of the use cases will fall. Here at the bottom, we see something called reinforcement learning. this is often used in robotics, or if you want to program an AI to play a game or something, you would have to design a reward function, something that tells the AI that if it's achieving the goal of the game or whatever it wants to do, and then it will try to find out strategies, actions to do which score a reward, or try to not find bad strategies, bad actions that don't score a reward or even get a negative reward, so that the machine by itself is going to learn a strategy to, well, play a game or do some robotic tasks or something like this. Another block is unsupervised learning. This is a case where we usually don't have a clearly defined label on our data, a thing that we want to predict, like a target variable that we want to predict. In unsupervised learning, the data is more or less working on itself, and there are use cases in dimensionality reduction or clustering. Maybe in our industry, especially interesting things could be customer segmentations, but there it's often not clear, is a customer definitely a part of segment A or segment B? So this is why it's called unsupervised. There's no exact variable that we're trying to predict, like a ground truth. In opposite to this, we have supervised learning, where we do have a ground truth variable, a clear target that we want to predict. We can do this continuously in tasks called regressions, and there are things like forecasting, for example, weather forecasting or market forecasting. There you clearly know the temperature yesterday and the temperature over the last couple of weeks, and you can use this historic data with this clear temperature label you want to predict to predict, let's say, the temperature of tomorrow. And you don't know it yet, but once the day comes, you will know how much degree it has been tomorrow. So there is a clear label that you can predict. And this can be done continuously in regression, but this can also be done as a classification task, where you're trying to predict one of potentially several given classes, so discrete classes. For example, I don't know, you do an image recognition task on a bunch of fruits, and you want to see, is this a banana, an apple, or an orange? You have some discrete classes that you want to classify. Or in more customer insurance related things, maybe you want to classify if your customer is interested in buying a certain product, yes or no. Later on, you will know if he bought this product or not, or if your customer wants to cancel his insurance contract or something like this. And this is also what we're going to do today with the ToxBlock project, basically trying to classify text into categories of toxicity. And I will talk in more detail about this later. Generally, there are many different types of algorithms or algorithm families that you can use in all of those tasks. One of them is called deep learning. And you can, like, there are deep learning applications in all of those fields, but we're today doing supervised learning classification with deep learning. And it's basically a special form of machine learning that uses deep artificial neural networks. Sounds a little scary. I have a sketch of this here. And artificial neural networks are in principle layered mathematical structures where you have an input layer where you send in any sort of data that you have. If you work on tabular data, those could be the columns of your table. If you work on image data, this could be the pixels of an image. Or if you work on text, like I'm doing in this case, this could be, for example, the words in a sentence, first word, second word, and so on. And then this input is sent into hidden layers. Now, this image only has one, but potentially there could be more hidden layers. And often there are a lot of hidden layers. And if there are a lot of them, it's called a deep neural network. And in principle, what happens here is you send whatever data point you have in through here, and it's multiplied with a parameter called weight. And it's this, after this multiplication, it serves as an input for this next unit. And now you can send all the other inputs from all the other input nodes in here as well. And you do this with all the hidden units. So you have a lot of these multiplication parameters, these weights. Well, you can apply a nonlinear function here if you want to. And then it goes on maybe through more of those hidden layers. And eventually it will go into an output layer, again, being multiplied with some of those weights. And then you get, for example, in the output, how high is the probability for each of those classes. Now we have six units in the output layer. Imagine you have 6 possible classes that you want to classify something into. And now we compare this output with the actual label that we have. If we train on historic data or on labeled data, well, we know what is the target variable that we actually want to predict, and we can see how far off are we. And this is usually quantified in something called a loss function. This is a mathematical function that tells us how wrong is our output compared to the real label. And initially, it's going to be very wrong because those weights are going to be initialized in a more or less random way. So in the beginning, whatever comes out here is going to be complete nonsense. Now we take this loss function that tells us how far we are off. And oh, I see someone raise their hand. Does that mean it's a question?
Is the target, is this something from the real world, or is this something like an is this something like a target model we built by ourselves?
Now, the targets in this case are usually labels. You can imagine, depending on the tasks, imagine you have some tabular data from insurance contracts, you know what product type it is, what's the prime being paid, those are the inputs. And then the target could be what product do I want to recommend to the customer to buy next.
Okay.
And this could be, I don't know, liability insurance or motor insurance or real estate insurance. And we would train this on historical data from our customers that have already bought this product. And then the target is telling us, did he buy it or not?
Okay, so the outcome will be a recommendation that we stress against.
Exactly, that could be the case. It could also be the case that the data has been labeled, which is often, for example, the case in image classification, that you have humans labeling, this is an image of a banana or this is an image of an apple. Or in text classification as well. Here, the data set that I'm using has been labeled by humans saying this is a toxic text or it's a non-toxic text.
Okay.
And this is what we compare this to. And we quantify it mathematically in this loss function, and then we differentiate this loss function with respect to all those weight parameters. So that's in German, that's called a partielle Ableitung. What we get out of there, we get a gradient. And now we basically follow this gradient to adjust these parameters, these weights. And we do this over and over again. This is called gradient descent. And in principle, we start somewhere where the loss function is quite high. We have a high loss. We are very far away from our target. Now we try to adjust these parameters by going down the gradients again and again. And hopefully our loss function will decrease until we reach some kind of minimum. And our weights will be adjusted in a way that if we send something in here, for example, the sentences, the words in a sentence, they go through all those multiplication operations, nonlinear function operations, and in the end, we get a classification out of here that is probably or hopefully very close to the actual target. And then the idea is, if we get new data that we haven't labeled yet, hopefully the classification of this model will also perform well on the new data. Is that clear?
Yeah, thanks.
Okay, great. This modeling is actually just a small part of the whole process. In the machine learning lifecycle or data science lifecycle, data is the most important thing because data is what we train these models on. You usually start by identifying something, then you often have to do some data pre-processing, removing data to make sure they have a certain statistical distributions, because some of those machine learning algorithms may be a little bit confused if the data doesn't follow certain distributions. And you would start building a model. You come up with an architecture that is interesting and train the model, and later you validate it to see if it performs well. And if everything is done and you're convinced that your model performs well, then often if you work in academia at a university, you think like, okay, that's great, I'm done, I have an output here, and I can publish this in a paper, and then afterwards I have to never care about this again. Now you want other people to use whatever you've created. You need to deploy this model somehow. You need to integrate it with other applications like CRM systems or whatever, so that they can use it. And you have to do some automation and maintenance. You have to monitor if your model keeps performing well, make sure that it doesn't drift off and at some point the predictions get bad. So the whole life cycle is actually pretty long. Yeah, so those are the machine learning basics. I hope I gave you an idea of how those processes work in general on a very high level. I would now get back to the actual projects if there aren't any questions. If you do have any questions, if you do have questions, just unmute yourself. If not, then I'll just continue.
Is it difficult to set up this gradient and weight mechanism?
It probably used to be pretty difficult when people started doing this the first time, but by now there are a couple of very sophisticated and easy to use libraries that you can use. For machine learning in general, a lot of different types of algorithms. There's a great Python library called scikit-learn. Generally, a lot of this machine learning thing takes place in the Python programming language because there are a lot of great libraries for those data processing tasks. Now for this deep learning, in particular, I think there are two very popular libraries called TensorFlow and PyTorch, and they take a lot of this work for you. So you can take a lot of those readily built components, so you don't have to actually code this entire neural network and this gradient descent and backpropagation yourself. They're usually pre-implemented building blocks that you then can stick together to build a neural network architecture that is going to be suitable for your type of problem. Probably more difficult and more manual work is still done in the whole data understanding, data exploration, data processing, and now for this toxic language classification, that's not really applicable, but if you work well in a company and you want to solve a certain business case, I think especially the business understanding and the data understanding the processes in your company to make sure that the data you use for this model is actually what you think it is and it's not complete nonsense that's going to come out on the other end. That is the tricky part that unfortunately no libraries is doing for you.
One other question, please.
Yeah.
Do we have a dedicated hardware to train the model in our company? Because this could be quite time consuming.
This could be very time consuming, exactly. Especially for deep learning, it often requires, if you build large models, you would probably want to do this on GPUs, on graphical processing units, that can do a lot of those matrix multiplication operations in parallel, and are much faster to do this as in comparison to CPUs. And I'm not aware that we have any hardware locally, but we can rent it in the cloud. So if we want to train very large neural network models, we could do this, for example, on Amazon Web Services. We can rent GPU infrastructure there, train the models on those GPUs, and get the trained model back. Okay, yeah, well, then I get back now to the actual thing I built here called ToxBlock. And it's a simple deep learning application for recognizing toxic language in English text. That's what I mentioned already. Why English, by the way? Because English is heavily oversourced. Most of the internet is in English, and it's just easy to get a lot of data in English. I think German should be fine as well, but if you go to some exotic languages, you're going to have a hard time actually getting a lot of data to train your models with. And why would anyone want to do this? What is this useful for? Well, you can use it to identify potentially toxic language and then block it or flag it for review, maybe by a human reviewer, in things like social media posts or comments or newspaper articles, or maybe comments on those newspaper articles, anything like this. And you may again wonder, why would anyone want to do this? This sounds a lot like censorship. This maybe sounds like something that a very authoritative government would like to do, but why could this be interesting for news article websites? Let me quote here. The threat of abuse and harassment online means that many people stop expressing themselves and give up on seeking different opinions. And this is a problem, especially if you want to be in a free country with a well-working democracy, where it's very important to find an opinion based on facts, on discussion, try to reach some consent. And of course, this happens online because most people read their news online now. And if you have people insulting each other in the comment section, no one wants to take part in this discussion. If you have a different opinion as some angry guy in the comment section, and you state it, and he just starts insulting you, you don't want to have this discussion anymore. So effectively, it shuts down meaningful discussions, and that's a problem. And that's not only what I see. It was also the content of a machine learning competition that took part, I think, about 2 years ago, on a website called Kaggle. That's a website that often hosts machine learning competition in cooperation with companies or academic institutions sometimes. So if you want to get started with machine learning, that's a cool place to have a look how this stuff works. And there are also some money prizes. In this case, it was $35,000 for whoever builds the best model that is very good at classifying toxic text. And they provided a data set here, which contained around 250,000 labeled comments that potentially belong into 6 categories of verbal toxicity. You have them here: toxic, severe toxic, obscene, threat, insult, identity hate. They could also be non-toxic, of course, like regular normal comments. And if they're really bad, maybe they could also belong to all 6 of those categories. So it's like a multi-class classification problem. And those comments actually originate from Wikipedia. I think if you want to write and edit an article in Wikipedia, there's a comment section so that the authors of the article could talk to each other. Sometimes people want to make some adjustments to their Wikipedia articles, which the community doesn't accept. And then people can get angry and insult each other. And that's actually exactly what this data set is about. If we look into how those labels are distributed, you can see, luckily, most of the comments are non-toxic, which makes sense, right? People discuss about how they can make the Wikipedia article better. However, quite a large proportion is also toxic in general. And then among the more specific toxicity labels, you can see there's quite a strong class imbalance, like threat occurs very rarely, luckily, identity hate and severe toxicity as well, whereas obscenity and insults occur relatively often. Generally, this imbalance makes it more challenging for machine learning algorithms to do a good classification. It's, of course, if there are a lot of non-toxic comments, it's easier for the model to assume by default that the comment might be non-toxic. Whereas if it sees very little examples of threats or identity hate, it's hard for the model to learn from very few examples and to be able to generalize well to new examples that it has never seen before. However, it worked quite okay in this case. So here you see some typical words that show up in insulting comments. Obviously, there are things like fuck and shit and suck, ass, whatever. Interestingly, there's also Wikipedia, which is not an insult, but since it's from Wikipedia Commons, I guess it's not a surprise. Also some bad racial insults, things like this. And if you look how a typical comment looks like, it's basically people complaining that their changes to the article haven't been accepted. You like protect the article and fuck it up, blah, blah, blah. I don't have the fucking time to argue. Now this is basically raw text that we try to classify here. And it's not a great idea just to put raw text into a machine learning level. You maybe first want to simplify stuff. And one good thing to start with is removing some useless things. In this case, usernames, definitely, because you don't want the model to classify who is a toxic Wikipedia user, but you want to classify the content. Maybe numbers may not be very important. Punctuation is often not very important. In this case, maybe exclamation marks might be interesting, but let's say in general, we take out punctuation. And a category of words called stop words. Those are words that don't really provide any additional meaning, like or the, or personal pronouns, or connecting or filling words that don't really carry a lot of meaning. So you might as well remove them to improve your signal to noise ratio. You can do some text normalization, like try to make things look the same by lowercasing them, by unifying abbreviations, and do some spell checking. And you can do some techniques called stemming or lemmatization, where you're trying to condense words that kind of mean the same thing into one word, like R is, well, it just means B, so you turn it into B, or car, cars, 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 cars. Well, it's just, the meaning is just car, so you try to reduce this and make it easier. Then you have to turn it into some kind of numeric representation. Oh, by the way, I didn't explain what is the difference between those two things. Stemming just means you cut the word off so that the stem comes out, and lemmatization is basically the same thing, except that the stem has to be a real word that actually exists. I actually didn't use this in my model because I tried it and it didn't give me better performance, so I didn't use it. But after that, after you simplify stuff, you want to put things into a numeric representation, because machine learning algorithms only understand numbers in a way. So what you usually do here with sentences, you tokenize them. That means you turn the words into like numeric labels, integer labels. Of course, make sure that the same words, like 2b in this case, also get the same numbers. And this basically builds your vocabulary. So you will have a mapping between what word has been turned into what number, but the numbers is what you feed into the algorithm. You can also create, like, do this tokenization with something called n-grams. And with these n-grams, you basically take, so n could be any number, like bigrams or trigrams. You try to take always like this is would be a bigram, is a would be a bigram, a sentence would be a bigram, which kind of helps to keep the meaning of words that belong together also together as one token. And this is often done in models where you don't really consider the order of a sequence of a sentence, but just like you throw the words together into something called a bag of words. But with deep learning models, we have special architectures that can actually handle sequences, like take the whole sentence in the right order, word by word. And to use this effectively in deep learning models, we often use something called word embeddings. And word embeddings, well, that's basically a mapping of these words into a high-dimensional vector space. So from one number, one dimension, you try to put this into a high-dimensional vector space. And in these images here, it's 3 dimensions, but in practice, it could be up to a couple of hundred dimensions. And you try to quantify semantic similarities between those words. And you can see it here. Semantic similarity, it means words that mean a similar thing, they should be represented by vectors that are close together in this vector space. And if they have a very different meaning, maybe those vectors should be far away from each other in the vector space. You can see here that the relationship between like king and queen should be similar as the relationship between man and woman. If you, for example, would take the queen vector, you would subtract the woman vector, and then you would add the man vector, the result might be very close to the king vector. Or here, same with capitals. So you should have a similar relationship between a country and its capital. So that if you would take Hanoi away from Vietnam and you would add Moscow, maybe you would end up with Russia. And these vectors are also learned parameters. So they are also in this whole model with this whole gradient descent, they're also being adjusted in a way that these semantic relationships are quantified in a meaningful way. To basically meaning of the word into this vector space. And then you can feed the entire thing into the actual neural network. And the type of neural network we're using here is called a long short-term memory neural network. I'm not going to explain in detail how that works. You could probably have an entire lecture on this. But it belongs to to a family of neural networks called recurrent neural networks. And those are the ones that can process sequences. And you can see it's layered here from the input to the output. So starting from the input, we're doing with our tokenized sequences. So now this basically represents our sentences or the comments in a numerical format. Then we put the entire thing into this embedding space. But we don't start from scratch. We don't start from completely randomly initialized vectors. We use something called pre-trained embeddings. And in this case, I chose one that is called GLOVE. That stands for Global Vectors for Word Representations, something developed by Stanford University, where they basically trained these embeddings on the entire Wikipedia corpus and other large crawls from the internet to make sure that these pre-trained vectors already have a good understanding of the English language. And I'm using this here as a base, and then keep improving is by keep training is for our special use case. So for the special thing we want to classify toxic comments here. So maybe there's a little bit twitching needed to make the performance even better, but we already start at a pretty good embedding by using this pre-trained embedding that has been trained on half the internet maybe. Then this whole thing is basically put into this neural network, the LSTM. And you can see here it's represented like cells process part of the sequence. If you would imagine this would be like a 3-word sentence, and you have the first word of the sentence, second word of the sentence, third word of the sentence, and whatever happens in the middle is a little bit too complicated, so I'm not going to go into it in much detail, but the interesting things are these connections between the cells. Basically, the second word can understand a little bit of the meaning of the first word, and the third word can understand a little bit of the meaning of the first and second word, and everything has been in the sentence before. And we can, with some internal parameters that are also being trained, how much of the previous meaning is going to be preserved in the next cell and how much is forgotten. And in the end, we do this bidirectionally, like we read the sentence from the front, we read the sentence from the back, concatenate it together, and put this sequentially processed part. We feed it into more or less like a regular neural network, like I've shown on a previous slide, where we have those weight connections that lead into a final output layer, where we have our categories of toxicity. And in this final output layer, we apply a function called sigmoid. That's basically just pressing the values between 0 and 1 so that they represent a probability. So everything we get out on these final units will be a probability for each of these toxicity classes. So that in the end, we know is the common non-toxic or is it toxic, and preferably also what type of toxic. That's a lot at once, and it's not horrible if you don't have. One thing that I might want to highlight again here, this model only has around 1 million trainable parameters. That is comparatively small for a neural network. Sounds a lot, but actually I could train this on my laptop in half an hour. So coming back on the infrastructure part, I didn't even need GPUs to train this. I could just do this on my network because it's very small, and this is why I wanted to keep it easy and simple so that I don't have to rent any infrastructure on the cloud. Yeah, so now we're done with the model. It's constructed. Now we would like to kind of bring it into other systems, make it communicate. And up to this point, I have everything done in so-called notebooks, more specifically Jupyter notebooks. This is a type of software where you can do, it's basically an interactive computing environment where you can execute code snippets, like you write a little bit of code into a cell, you execute it, and you can see the output. And that is maybe not easy to understand for people who haven't used it, so I'm just going to show you a demo very quickly. Quick question, can you see my browser?
Yes.
Yes.
So I have an example of a Jupyter notebook. Yeah, what? Okay, this thing is annoying me now. It apparently crashed. Crap. So, okay, well, I was preparing this in advance. I can, this is a little bit annoying now. Of course, this happens when I give a talk. Anyway, it's an interactive computing environment where in principle you can have text cells where you can write things in Markdown and you can document things as text, and you can see you can embed hyperlinks and everything. You can embed images and graphs, and it's basically very good for computation. But you can also add code cells where you can type in any statement and it's gonna execute it, and it should give you an output if it was running, which it is not right now. Sorry. Well, anyway, I hope you have a rough idea of what this is about. It's very good for experimentation because you can always do transformations on your data and you can see what comes out, and you can build a model and score and see the outputs. And it's also good for documentation because you can always write what was your thoughts. You can link to other websites. You can link to graphs or put in images. But it's kind of horrible to maintain and test and extend because it's this very linear flow. It's also a little bit dangerous because it stores variables, the state of variables. So you could execute this in a non-linear fashion, and you could mess it up a little bit. But it would require always a little bit of workaround if you want to like make this modular and export functions from it and test those code cells individually. So what should be clear to every regular software engineer, but maybe not clear to a data scientist that just came from university, is that you should probably use, regular Python and object-oriented principles and build proper data pipelines. Just regular object orientation, build classes, let them estimate from base classes, and try to put things into an API with methods that are similar over similar classes. Make the whole thing modular so that you can extend it easily, that you make it reproducible, that it's easy to test it. PyTested, for example, is a great framework for doing this in Python. And also, this makes it easy to review by your colleagues, easily version controlled, which on the other hand, with those notebooks is a little bit messy to see proper differences in what has your colleague changed in this source file. So bringing everything into this kind of regular, well-engineered best practice code makes everything a lot easier once you have a standing concept for your model. And then let's assume you're done with it. You want to package this up somehow. We have all the folders containing config, data, the models, the trained models, and some entry point scripts here. And then in Python, if you want to package something, you usually would use the setup tool. So you had a setup file in which you specify package info, version infos, you specify all the requirements that the thing needs to run. But this only includes code. So if you want to include non-code files, which you need to do in this case, because we have our pre-trained models and we want to provide them so that people don't have to retrain the thing if they want to start using this on their own. You can also include this in the manifest files where you can put in any file or any documentation that should go into this distribution. Sorry, let me have a sip of water. Then you can use the setup tools to just create a distribution from your model, or from your project. For example, a source distribution where you have the script, but also a compiled binary version, which is nice if you can provide this so people don't need to build their own binaries when they download your package. And you can upload it to some package index registry. Of course, you can use a private one if it's like sensitive code and you don't want it to be public. But since this package here is totally open source, you can use the Twine Python library, which uploads things to the Python package index. And that's like the most popular public index where you can get Python packages from. And for those who have used Python before, you probably have pip installed something. So pip is the package installer for Python. And if you don't specify any other URL, it usually tries to get things from those Python package index. And that's how you can actually get it. So pip install ToxBlock. You could do this in your Python application, and then you would get my ToxBlock package. So this is cool. Now we're at the stage where whatever other thing we want to write in Python, any other application could now use this by just locally importing this Python package called ToxBlock. But maybe a better idea would be to host this entire thing as a web service, as a web API. Like the API, the way it looks like would be very similar. Well, if we would use this locally, just we import ToxBlock as a Python library, and we import maybe its predictive capabilities. Make a single prediction function. We write some nasty insults inside. And then we call this function and we get back a Python dictionary that shows us the probabilities, the predictions of how likely it is that this text will belong to one of those toxicity classes. Now, if you have this online as a web service, the whole process would be looking pretty similar. You have some URL, some endpoint against which you send an HTTP post request. You put some JSON data in the body, the input data, the same insult, and you get back a JSON object that looks very similar. Basically, the prediction for each of these toxicity classes. So why is this a cooler idea to do it this way? Well, APIs in general, application programming interfaces, and this is also an API that I provide here. It's like applications can communicate with each other as if they had a contract. You know what kind of methods, what kind of functions you get, which you can use, and it's specified what you get back. So that's a better idea than just like copy pasting source code into your source code again, changing things up. So you have a clearly defined contract, and you don't need to care about everything that goes on. You just have like those API functions exposed to you as a user. But doing this as a web service removes all language barriers. Now you don't have to write some Frankenstein wrapping code to include Python into another language. I think every language probably has some HTTP clients available. So now this you can call from anywhere, everywhere over the internet, and you can administer this in a central way. So you can basically have one thing in the middle and integrate it with all your other applications. Maybe you have different front ends, a web app, a mobile app, iOS or Androids, and they just all call the same API endpoint. And whenever you want to change something, you can do it centrally, and there's only one place. So that's very convenient. And it's a common way to deploy the predictive capability of machine learning models. There are also other scenarios where maybe you want to do a prediction on your entire database. So you just do a batch job, and whatever you predict, you write it back into the database. Or something that has to go very fast on a mobile device, and maybe then it makes more sense to include the machine learning model really on that mobile device. But providing it as an API endpoint is a pretty common compromise between those things. But then how is it actually built? What is the stack that I'm building it on? Well, I have this ToxBlock package, which is now on the PyPI, the Python package index. You can download it from there. Now I kind of have to wrap it with some routes. So I do this with Flask, which is a pretty easy to use micro web framework for Python. And in my Flask app that I'm building, I'm just importing again the ToxBlock package, and I provide a function which is decorated with this routing parameters here. If there is someone who sends a post request to this URL endpoint, then invoke this function, make predictions, and then you get the data from the JSON that has been sent in the request. You do some validation, and if there's no error in the validation, then you do the prediction, and you just return this prediction here in this dictionary. So this Flask is then returning this in the HTTP response as a JSON object. Now Flask itself has a very small development web server, but it's I see a weird. I hear a weird music in the background. Could you please all mute yourself?
It comes from Starleaf. Perhaps you have opened this Starleaf app open.
Oh, I do. In fact, yeah.
Yes.
Sorry.
Already.
Okay, sorry. Sorry for this interruption. I'm going to continue. So the whole thing is built on another web server that is much more potent than Flask and can take a lot of requests in parallel. It's called GUnicorn, and up to this point, this is all written in Python. Everyone who has probably developed in different environments in dev and production knows that it can be a pain to get all the dependencies right. So I'm putting the whole thing into a Docker container. So that's like a virtualization that takes care that all the dependencies are wrapped together. And in the end, I push this to a container registry on Heroku. It's a platform as a service, like a cloud provider that has a nice free tier. I'm pushing the Docker image there, and then I'm deploying it there, and then it's basically online. And that's pretty much it. So I would say now is demo time. And if you would like to, you could now post some nasty language, some insults or something into the chat, and we can test it here. Do you all see my browser again?
Yes.
I hope yes. Great. If
Yes,
you want to
all
play
good.
with this, yourself, I made a little website for this project. You can check it out here. There's also links to GitHub repository of ToxBlock and its API, link to the PyPI website. So here is also a little instruction manual if you intend on using this. And there are links to blog posts that I wrote on ToxBlock and the API. Right, and here's a thing that you can test. So, little demo. Hello, you little shits. So what this is doing now is it's just doing a post request to the API. And now I see some people are already posting some insults in the chat. We can make a little competition out of this. Whoever gets the highest toxicity score wins. So now something from Malte. Okay, this is already better than what I tried. It's clearly obscene. It's, well, definitely toxic. Pretty much an insult, but not very severe toxic, not a threat. Let's see what else we have. Daniel is saying, get out of my face. Oh, wow, that's okay. That's not very toxic. Not an insult. Why? Carsten, no, I don't think this is gonna get a high score. Why 2020 might be the horriblest election ever. I'm not sure if this is a word. Oh, well, no, this gets 0. Sorry, Carsten. I'm fed up with you. So maybe you already realized that if you're not using some actual like dirty words, the classification is not going really high here. This is probably mostly because eat my shorts. Oh, that's cool. That's probably mostly because we can, you know, some things like get out of my face or this is the worst election ever. This is something you could state in a discussion without really insulting people. Okay, eat my shorts. What about eat my ass? Oh yeah, that works better. Yeah, so you can see the model mostly grabs some actual insulting words. You are as thick as short. Oh, I like this. There are some very good suggestions here, but not very high scores. Right. What I was about to say, I think it very much gets certain keywords. If you have certain keywords, it's usually easy to trigger one of those things. For example, it's high to get the threat up, but if you tell someone, I will kill you, oh, 102%. Okay, that doesn't even make any sense. But it also sometimes gets absolute nonsense. Some weird bug that I found, if you write banana 100 times, it will also consider this as toxic. Which, oh, there's a good one. Someone took your head off and shit in your neck. Oh, sweet, that gets a very high obscenity score. Yeah, so this is a fun thing to play with. Your customer service sucks. Oh, not bad, at least high toxicity. Cool. Well, up to here. Any questions? I think we're looking at the time. We probably have to come to an end relatively soon. 5 minutes left. So yeah, at this point, do you have any questions or remarks or ideas?
Do you have any hint regarding the riddle?
Oh, yeah, I do. I actually have a magic potato for you that will reveal it. The password is NLP. Any questions regarding this project or machine learning in general or natural language processing in general?
Hey Pascal, thanks for the great talk. I have a question. How difficult it would be to make German possible within your application, as this probably is the most common language within our customer service products, for example.
Oh, absolutely. I think the trickiest thing is always getting the data. In this case, I was very fortunate that I found this human labeled data set online at Kaggle, which contained a lot of hand-labeled, human-labeled comments. So if you want to do the same, make the same thing possible in German, I think you would just need a data set like this. So I'm not aware of a toxic German language data set that is freely available on the internet. But if we wanted to implement this for our customer service, we could label it ourselves. Like we could try to see all the messages that are ever sent to our customer service. Maybe we can try to create some artificially toxic ones ourselves. And then we need someone who labels this stuff. Once we have the targets, then it should not be any problem to do the same thing in German. Also pre-trained word embeddings do definitely also exist for German and other large languages. So once you have the starting data set, shouldn't be any problem. So thanks, was a good question. In general, that's true for any languages, but as I mentioned in the beginning, some languages are a little bit under-sourced because there are not so many speakers, or at least not so many speakers active on the internet. Well, if there are any more questions that come up afterwards, feel free to contact me anytime. Yeah, the password for the riddle is NLP, all caps. And thanks a lot for listening. I'm glad to see that a lot of people took interest in this, and there were a lot of participants in this meeting. I'm also going to end the recording now. And yeah, thanks a lot for your attention.